This is my demonstration of proficiency project for the course Nutrition 831. The title is The Microbiota Gut-Brain Axis and Major Depressive Disorder. Part 1, Physiology and Pathophysiology and Mechanisms by which eubiosis and dysbiosis affect major depressive disorder. Major depressive disorder is one of the most prevalent psychiatric disorders. It affects approximately 264 million people globally. Neurotransmitter imbalances may be an important part of the disorder. Patients with major depressive disorder also experience chronic stress, which reflects a hyperactive HPA axis. Major depressive disorder may be influenced by altered circadian rhythms. It has been associated with increased inflammation and oxidative stress. Gut microbiome imbalances. The gut bacteria imbalances may be a factor in the etiology. Major depressive disorders may shift the gut microbiome from a eubiosis to a dysbiosis state. A systematic review found that there were no significant differences in alpha diversity, which is the richness and evenness of species, between major depressive disorder cases and controls, but there were consistent differences in beta diversity, which is the composition of communities between cases and controls. Gut-brain axis. The gut-brain axis is an important bidirectional system that links the enteric nervous system in the gut to the central nervous system via the vagus nerve. The ENS consists of nerve bundles and ganglia that span the whole length of the digestive tract, and it has been referred to as the brain within the gut. The vagus nerve uses intestinofugal neurons for communication between the ENS and the CNS. Afferent signaling is used for gut-to-brain communication, while efferent signaling is used for brain-to-gut communication. Through the vagus nerve, changes in GI functioning can contribute to the pathogenesis of major depressive disorder, underscoring the gut-brain axis's role in psychiatric conditions. Intestinal permeability. Intestinal permeability typically results from gut dysbiosis and may play a role in the pathophysiology of major depressive disorder. Intestinal permeability is characterized by a compromised gut barrier, which allows bacterial products, lipopolysaccharides, and toxins to pass through the gut wall into the bloodstream. This can trigger systemic inflammation and activate the immune system, which can negatively impact the CNS. Patients with major depressive disorder had high levels of IgM and IgA antibodies, which reflect an immune response to translocated bacterial products. Psychological stress, as well as a high-fat diet, was shown to contribute to intestinal permeability. In terms of short-chain fatty acids, these are produced by bacterial fermentation of dietary fiber. They have a neuroprotective effect. Short-chain fatty acids may also contribute to blood-brain barrier health. Propionate protects against blood-brain barrier permeability. Butyrate may protect against intestinal permeability. A strong blood-brain barrier as well as a strong intestinal barrier may protect against major depressive disorder. Neurotransmitters. Major depressive disorder may be linked to dysfunctions in many neurotransmitters, including serotonin, dopamine, norepinephrine, GABA, and glutamate. Neurotransmitters and neurotransmitter precursors are synthesized in the gut by bacteria. Some of the neurotransmitter precursors produced by gut bacteria include acetate, choline, tyrosine, L-DOPA, 5-HTP, tryptophan, and phenylalanine. These neurotransmitter precursors are used to synthesize neurotransmitters in the gut, or they can travel to the brain via the bloodstream and cross the blood-brain barrier, where they can be used to synthesize neurotransmitters in the brain, including glutamate, GABA, acetylcholine, dopamine, serotonin, norepinephrine, tyramine, phenylethylamine, and tryptamine. Neurotransmitters such as serotonin and dopamine, in addition to affecting mood, can also influence gut motility and gut bacteria balance, highlighting the bidirectional nature of the gut and the brain. Part 2, how these pathways and mechanisms align with the core physiologic domains of the functional medicine matrix. For assimilation, the pathways and mechanisms are The gut microbiome plays a role in the absorption and metabolism of nutrients from food. Dysbiosis may impair gut bacteria-mediated processes related to nutrient metabolism, neurotransmitter synthesis, and short-chain fatty acid production. The diagnostic considerations are small intestinal bacteria overgrowth may be a clinical sign and symptom related to dysbiosis. SIBO can contribute to nutrient malabsorption. Vitamin B12 as an example. Dysbiosis may be associated with celiac disease, non-celiac gluten sensitivity, and irritable bowel syndrome. Tests for malabsorption, celiac disease, IBS, as well as a micronutrient panel can be performed. For structural integrity, the pathways and mechanisms. Structural integrity may refer to the integrity of the gut barrier, which is made up of tight junctions. During intestinal permeability, bacteria and toxins pass through the gut wall into the bloodstream, triggering inflammation and activating the immune system, which can negatively affect the CNS. Gut dysbiosis can trigger intestinal permeability and alter tight junction proteins, including claudin 5 and occludin. For structural integrity, the diagnostic considerations are disorders associated with intestinal permeability include food allergies, celiac disease, Crohn's disease, type 1 diabetes, and possibly others. For testing, the lactulose mannitol sugar test can be used to assess intestinal permeability. A higher lactulose to mannitol ratio indicates increased intestinal permeability. Stool tests that measure zonulin concentration can also be used to assess intestinal permeability. Zonulin is a protein that regulates tight junctions, and elevated levels in stool indicate intestinal permeability. Communication, the pathways and mechanisms. The neurological pathway involving neurotransmitter functioning in the gut and brain is relevant to this domain, since short-chain fatty acids are used to synthesize neurotransmitters both directly and indirectly. Impaired production of short-chain fatty acids due to inadequate fiber intake could lead to lower neurotransmitter production, which could manifest as major depressive disorder symptoms. The diagnostic considerations are the clinical signs and symptoms of major depressive disorder include chronic low mood, sadness, melancholy, anhedonia, sleep issues, lack of focus, fatigue, altered appetite, weight changes, and chronic stress. For testing, psychological depression screening tools such as DSM-5, HAM-D, HDRS, MADRS, or BDI-2 may help to diagnose major depressive disorder. ACTH and cortisol tests may be used to determine if there is HPA axis dysfunction and stress. For energy, the pathways and mechanisms. Patients with major depressive disorder typically have lower energy levels and are thought to have reduced mitochondrial energy output. It appears that there is bidirectional communication between gut bacteria and mitochondria, and impairment of mitochondria may affect gut bacteria composition. Vitamins are needed to produce energy, especially B vitamins, and can be obtained from food or synthesized from gut bacteria. Diagnostic considerations. Clinical signs and symptoms include low energy or fatigue. Organic acid testing may be used to determine if there are mitochondrial respiratory chain dysfunctions that may affect energy metabolism. For defense and repair, the pathways and mechanisms. The immune and inflammatory pathways are relevant to this domain. Gut dysbiosis may increase inflammation by activating the immune system, which could contribute to major depressive disorder symptoms. Intestinal permeability is a mechanism that can trigger systemic inflammation and immune activation. Patients with major depressive disorder had increased levels of IgM and IgA antibodies, reflecting an immune response. Neurotransmitter precursors are produced in the gut and may play a role in immune function. The diagnostic considerations are that it may make sense to test for systemic inflammation and more specifically pro-inflammatory cytokines. It appears that the ELISA is a blood test commonly used for this. Also, it appears that saliva can be used to measure inflammatory cytokines, including interleukin 6, 8, 1 beta, and tumor necrosis factor alpha. For mitigation and clearance, the pathways and mechanisms, there is a gut microbiota liver access and crosstalk between the gut microbiota and liver. If there is gut dysbiosis, this may impair the liver's ability to detoxify harmful microbial byproducts. Gut dysbiosis combined with low dietary choline may promote trimethylamine N oxide, TMAO, in the liver, which is toxic, and this may impair the liver's detoxification and clearance capabilities. Additionally, intestinal permeability may result in increased levels of lipopolysaccharides translocating into the portal vein and liver, contributing to liver inflammation. Additionally, impaired liver function and altered species of gut bacteria are linked with slowed gut motility, which could contribute to constipation, which could impair clearance. The strength of the gut barrier is closely related to the liver's detoxifying capacity. The level of intestinal permeability is closely linked to liver function impairment. For diagnostic considerations, liver function tests including ALT, AST, ALP, and GGT may indicate impaired detoxification capacity and liver disease. A clinical sign and symptom of inadequate clearance may include constipation. The Bristol Stool Form Scale can be used to assess this. Part 3. Review the evidence for nutritional interventions, clinical evidence for benefits in major depressive disorder, emphasizing interventions that work directly on dysbiosis or its sequelae. Nutritional interventions play an important role in preventing and improving symptoms of major depressive disorder. The microbiota gut-brain axis is significantly affected by diet. The Mediterranean diet appears to be the diet that has the strongest support for lowering the risk of major depressive disorder and improving symptoms. This diet consists of high amounts of fruits, vegetables, legumes, whole grains, and extra virgin olive oil and fish. This diet is high in micronutrients that have antioxidant and anti-inflammatory properties. The polyphenols have antioxidant properties, while the monounsaturated and omega-3 fatty acids have anti-inflammatory properties. As such, these anti-inflammatory effects may contribute to eubiosis. The Mediterranean diet may contribute to gut bacteria diversity and a healthy balance of gut bacteria, which is linked to lower levels of depression. The carotenoids in the Mediterranean diet, such as lutein and zeaxanthin, were shown to positively influence the composition and increase the diversity of gut bacteria. Commensal bacteria were increased, including bifidobacteria, lactobacillus, Faecalibacterium presnitzii, and Bacteroides. There was lower proteobacteria, which is pro-inflammatory. The Mediterranean diet also includes high amounts of fiber, which also promote gut bacteria diversity. Gut bacteria adapt to changes in diet within 24 hours of eating, so it doesn't take a long time. The polyphenols and polyunsaturated fatty acids may contribute to antidepressant-like effects. Fish contains EPA and DHA, which support serotonin and dopamine signaling, neuroplasticity, the generation of new neurons, as well as help regulate the stress response and HPA axis. Foods high in vitamin B9, folate, and B12 may support neurotransmitter production and have antidepressant-like effects. Legumes in the diet provide a source of tryptophan, which is required to synthesize serotonin. Dietary tryptophan, after being absorbed in the gut, travels through the bloodstream and passes through the blood-brain barrier, playing a role in the production of serotonin in the brain. Tryptophan can also be used by the enterochromaffin cells in the gut to produce serotonin. It may also be metabolized through the kynurenine pathway in the liver. Legumes also contain zinc, which is an NMDA receptor antagonist that can protect against glutamate excitotoxicity. Additionally, the Mediterranean diet may lower the activation of the tryptophan kynurenine pathway, which may increase serotonin levels and lower the production of metabolites that are neurotoxic. The Mediterranean diet increasing short-chain fatty acid production is backed by multiple RCTs, and short-chain fatty acids have been shown to promote gut barrier integrity, decrease intestinal permeability, and lower inflammation. Fiber in the diet feeds bifidobacteria and lactobacilli, which are used to make short-chain fatty acids. Foods high in fiber include fruits, vegetables, whole grains, and legumes, and foods high in soluble fiber include apples, citrus, and oats. Recommendations for lowering inflammation include consuming 5 servings of fruits and vegetables per day, consuming nuts and seeds, black tea, green tea, and the caffeine in coffee, resveratrol-containing foods such as berries, grapes, and red wine, curcumin, found in turmeric, citrus flavonones, soy isoflavones, walnut flavanols, tea and cocoa flavanols. Prebiotics and probiotics may help lower brain inflammation. Antioxidants such as vitamin C, E, D, and glutathione. Plant foods in the Mediterranean diet may contribute to a better bifidobacteria to E. coli ratio, which is thought to lower GI inflammation. Extra virgin olive oil has been shown to increase beneficial bacteria that generate anti-inflammatory compounds. Examples of how diet can support neurotransmitter functioning: psychobiotics, which are specialized probiotics that have mental health benefits, may increase the amount of tryptophan, which is converted to serotonin. EGCG, which is found in high amounts in green tea, has been shown to increase serotonin levels. Also, green tea contains chlorogenic acid, which can inhibit monoamine oxidase A, which reduces the breakdown of neurotransmitters. A ketogenic diet may increase the amount of glutamate available for GABA production, which may help with GABA signaling. In terms of macronutrients, the recommendation is to increase protein and fat consumption and limit carbohydrates. Also avoid animal protein since it promotes bilophila, which is linked to intestinal permeability. The low FODMAP diet may help improve major depressive disorder symptoms, potentially through modulating the gut microbiome. Fermented foods may nourish the gut and improve dysbiosis. In terms of dietary supplements, 1 to 3 grams per day of fish oil containing EPA and DHA is recommended. However, less may be needed if there is adequate fish consumption. Vitamin D supplementation, 5,000 IUs, may be considered, as vitamin D was shown to improve dopamine signaling as well as HPA axis function. S-adenosyl methionine, which is SAMe, supplementation has been shown to be beneficial for patients with major depressive disorder. Supplements containing beta-carotene, vitamins A, C, E, and polyphenols may also be beneficial. To conclude, these are examples of diets, specific foods, nutrients, and supplements that may lower the risk of major depressive disorder or improve clinical outcomes. Many of them affect the gut microbiome, which can lead to improvements in major depressive disorder symptoms. And this concludes my presentation. Thank you.